So field emission, thermionic emission, field emission, and photoelectric emission. Thermionic emission means, so there will be a, like, a filament. When you heat the filament, then what happens? Electrons are emitted outside. So there are different ways by which we can obtain electrons. There are different ways by which we can obtain the electrons. Okay, so this is said to be thermionic emission. Field emission is like, cathode rays. Simple example for field emission is cathode rays. Okay, cathode in the tube light. Okay, tube light is the best example for that. Like between the two plates, like cathode plate and anode plate, when you apply a very high potential, so what will happen? Electrons, electrons will go towards from negative plate to the positive plate. Understood? Third one is photoelectric effect. What is photoelectric effect? When light of certain frequency incidents on the metallic surface, electrons are emitted outside. Okay, of light of certain frequency incidents on a metallic surface, then what will happen? Electrons are ejected outside. So this phenomena is known as photoelectric emissions. Okay, this was first done by, this was Hertz experiment. Okay, this was done by Hertz, then Hallbach and Lenard's observation. So this was first found by Hertz. Okay, Hertz experiment is there. So he took the same thing. Just he took some ultraviolet light, and he made that ultraviolet light to make the incident on the photographic plate, some metallic surface. Then electron came out. Then later on, this was studied by Albert Einstein. Okay, Albert Einstein, if you see, year 1905 was celebrated as year of physics. Year 2005 actually, not 1905. 2005 was celebrated as year of physics. This is exactly after 100 years. 100 years of the contribution. It's not the date of birth of Albert Einstein. It is actually 1905. 3 famous papers were published by Albert Einstein. 3 famous papers were published. Number 1, it is about the photoelectric effect. One is about photoelectric effect. The second one is E is equal to mc square. Third one is Brownian motion. Brownian motion? Somewhere you studied the lower classes, right? Brownian motion. Okay, it is in okay. Brownian motion is not there. We didn't study this Brownian motion. It's like a very simple concept. It's like what he has done is like he has taken some pollen grains in the water. Then after some time they started moving in a chain. All these pollen grains. Then he thought like pollen grains are organic substances. They are organic substances. That is maybe there is a reason they formed the chain. But then he tried with the gas particles also. They also started moving in the chain. What he did is, he took a cell, a glass cell. In that there was some gas and smoke particles. All the smoke particles, and he viewed through the microscope. And he put the light. This is the glass cell, and he put the light from here, and he saw from here. And the microscope was placed here. So then he saw that all these smoke particles they formed a chain. This particular motion is known as Brownian motion. Okay, so he discovered that. So and also in 1906 he published one more paper, that is theory of relativity, special theory of relativity. But no one could understand this thing. Theory of relativity was not understood by anyone in the beginning, but later on people understood. Actually, he got his PhD on photoelectric effect, and also his Nobel Prize also on the same topic. Actually, he was supposed to be given on theory of relativity actually, because at that time no one could understand what is theory of relativity. Okay, the actual contribution was this one actually. Very good contribution to physics was theory of relativity. Understood? So that's the thing. Okay. So now, so this after 100 years of its publication, okay, so this was celebrated as Year of Physics. Understood now? So, so photoelectric, his PhD got it. You got the idea? So that's the importance of photoelectric. If you see at the in those times, the thesis means we have a book actually. We need to get a PhD when we get a doctorate. We have to whatever the research we do, we have to write a project book, like book. Okay. The thesis what we say. So it's not just passed like that. It is sent to different scientists or professors. They will go through it, and when it is perfectly okay, then we'll be awarded. And after that, we'll be asked many questions regarding the topic. Then, if they are satisfied with that, then we'll be awarded the degree. Especially in sciences, it is little difficult. Otherwise, the other subjects is little simple. Right? Sciences, because you need to do it experimentally. You need to prove it experimentally. That's the problem with challenge comes with the science. Otherwise, it's okay. Now, so, now what is photoelectric effect? He said that when light of certain frequency, okay, I'll write the definition here. So, photoelectric effect. So, when light of certain frequency, when light of certain frequency is made to incident, is made to incident on a metallic surface, electrons are ejected out. Electrons are ejected. This phenomena is known as photoelectric effect. Okay, this phenomena is known as photoelectric. Clear? The light of certain frequency is made to incident on a metallic surface. Electrons are ejected. This phenomena is known as photoelectric. Clear? Okay. Now, clear? So we'll go ahead. There are 4 graphs that is very important. That explanation of 4 graphs is important. Then only the graphs are, we have to focus more on the graphs. There is no such like formulas here in this particular thing. Okay, very less formulas are there. Let me just explain the experimental thing. Okay, so let's try this. You want this? The copy this photo? Yeah. Okay. Okay. Now, see, this is the experimental setup of photoelectric effect. How to do this experiment. Now, this is a vacuum evacuated classroom, and this is a quartz window. This opening, this is a quartz window. Quartz plate is there. Now, this is the source. Light is made to incident on this negative plate. This is a cathode plate, photosensitive plate, that is cathode plate, and this is anode plate. Okay. Now, what happens is this cathode and anode is connected here. This is the commutator. Okay, this one is commutator. Clear? Now, and it is here there is a microammeter which is in series. Ammeter, in the simple words, there is ammeter. Ammeter in that there is a family: milliammeter, microammeter, nano, or galvanometer. Okay, so in the ammeter we have a family: milliammeter, microammeter, okay, or galvanometer. Okay, to detect the current. So they are all connected in series. Micro means 10 to the power of minus 6. Minus 3. Milli means 10 to the power of minus 3. Micro means 10 to the power of minus 3. Galvano means 10 to the power of minus 3. Just to detect the current. For that purpose we use that. Okay. Nano, instead of saying nano ammeter, we are saying galvanometer. Understood? Instead of saying nano ammeter, we are saying galvanometer. So it is only used to detect the current. To detect the current or to measure a current of very minute value, okay, magnitude. Now, voltmeter is connected in parallel. There is a rheostat here and there is a battery. Sir, why do we connect a battery here? The purpose is to make the one plate as negative, the other plate as positive, only for that reason. And this is vacuum evacuated. Why do we remove the gas, whatever the other gas is there? Why do we remove that? The reason we are pumping out the gas. If any gas is there, we are removing that gas. What is the reason behind it?
Below at a certain speed.
When the electrons are moving, there is a possibility that they can ionize the particles which are present in the path. Understood? If any other, suppose there is hydrogen gas, oxygen gas, or some other gas, so there is a possibility that these electrons, when they are moving fast, they can ionize the gas particles present in the gas chamber. For that reason, we do that. Okay, is that clear? So now this is a commutator and this is a rheostat. Okay, now the first graph we will do this. Understood this one? So what happens? Electrons will light passes through the quartz plate. It hits the surface, cathode plate. Then electrons are ejected out. Okay. So the first thing, it depends upon the frequency. First concept depends on the frequency. And to make you understand, I'm not going in infrared and infrared or UV region. I'm just trying to explain with my visible region. This can be easily understood. Okay. So I will be taking only VGR colors for time being. It doesn't mean that it is only available for visible region. It's also possible for ultraviolet also. But I don't know exactly. Ultraviolet we haven't seen. We can only feel. Infrared and ultraviolet we can only feel, but we haven't seen that. But it is easy to differentiate with the visible color. Now we'll start with the first graph. The first graph is intensity of light versus photoelectric current. Intensity of light versus I think you will not come again. Sorry.
I think he has
chemistry
exam
tomorrow. He's focusing on that. Okay. Now, so here we have intensity of current, intensity of light, intensity of light versus photoelectric current. Photoelectric current. Intensity of light versus photoelectric current. So if you draw the graph is like this. It doesn't mean, first draw that, complete that drawing, then we can go ahead. Yeah. See here, it doesn't mean that as I increase the intensity, suppose these are the Big-J currents. So R is having low frequency or high frequency?
Oh,
Red color, red color.
Has the lowest
Lowest frequency and highest
highest
wavelength. Wavelength. And violet is having
lowest wavelength and
lowest
highest
frequency.
frequency.
Very good. Lowest frequency, lowest wavelength and highest frequency. Now it doesn't mean that if I just increase, suppose for red color light, no electrons are ejected out.
It's just
Okay.
very few.
No, maybe there is a particular curve for which electrons started coming out. It is dependent on the frequency, not on the intensity. Suppose I have the GR color. Suppose I'm starting with red, then orange, then yellow, and then green. Example. Okay. I started with this red color light, no electron came out. Even if I increase the intensity of light, nothing will come out. Suppose I have incident red color light on this one, then no electron came out. Even if you increase the intensity of red color light, okay, if you increase the intensity of then also, electron is not going to come out. Understood? Maybe for yellow or green, it started. Maybe I'll take for yellow. For yellow, what is happening? Electron started coming out. Understood now?
Yeah.
That means photoelectric effect took place. Now suppose if I am increasing the intensity, what will happen? More electrons will come out. Understood now? It is first dependent upon the frequency. If the frequency, it depends upon the frequency now. Okay. So it doesn't say that suppose for red color light, electrons are not coming out. Even if you increase the intensity, nothing is going to happen. No electron is going to come out. Is it clear? Yeah. Now, if I increase the intensity of light, more and more electrons. So once, suppose we fix a curve, maybe for yellow color light, electrons started coming out. Then you increase the intensity, more and more electrons will come out. Understood? So this graph is going with that. Okay. Intensity of light versus photoelectric current. This is for yellow. Suppose example for yellow color light. As you increase the intensity of light, photoelectric current also increases. Okay, that is detected where? In the microammeter. Understood now? So this is the first graph. This tells about the first graph. So here we'll tell about the first definition, threshold frequency. Threshold frequency. This is the minimum frequency. Right. I'll write the definition. It is the minimum cutoff frequency nu naught below which the minimum cutoff frequency mu 0 below which ejection of electron is not possible. Ejection of electron is not possible. This called threshold frequency. Threshold frequency or cutoff frequency. Okay, threshold frequency or cutoff frequency. At that particular frequency, electron starts coming out. Okay, this particular frequency is known as threshold frequency. This is very, very important definition. Okay, now after that, is it clear?
Yeah.
Now what we are doing in the second graph, we'll go with the second graph. In the second graph, he tells about that is effect of potential on photoelectric current. So I'll just write about this graph also. He says that the number of photoelectrons, please write this, number of photoelectrons, okay, the number of photoelectrons emitted per second is directly proportional to emitted per second is directly proportional to the intensity of incident radiation. To the intensity of incident radiation. Intensity of incident radiation. See here, the number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation. But the condition is it first depends upon the frequency. It depends on the frequency. Okay. Now, next one is effect of potential on photoelectric current. Let's finish off this. Did you write this? Okay. So, now, effect of potential on photoelectric current. Effect of potential on photoelectric current. Effect of potential on photoelectric current. So the graph goes like this. Okay. If you look at the graph, collector plate potential, photoelectric current. This is minus V0. This is 0. This is photocurrent. And this one is collector plate potential. And this is retarding potential. Collector plate potential and retarding potential. This is I1, this is I2, this is I2, intensity. Okay. And this is this one is to be stopping potential. This one is to be stopping potential. Now, see here. Now we have cathode plate and we have anode plate. Okay. This is, let it be minus 5. Let this be plus 5. Okay. There are two plates, cathode plate and anode plate. Minus negative 5, positive 5. Now here. Now we are reducing the voltage potential of this. Voltage means potential difference between the two, that is known as voltage. But here we say potential. If you are speaking only about one plate, we say it is potential. Negative potential, positive potential. Now here this is positive potential plus 5, and we write here plus 4, plus 3. We are decreasing the potential. Okay. Now plus 2, then now plus 1 volt, and then 0. Then slowly we are reducing it. So when we are reducing it, see, suppose we have taken one particular intensity. Okay, we have 3 intensities with us now. Okay, let this be Let this be I1, let this be I2, and let this be I3. Okay. So here we have three intensities, I1, I2, and I3. Three intensities are with us. Now suppose for the first intensity, now when I am reducing the potential, when I brought it to zero, doesn't mean that the current is zero here. Still the electrons are taken by the anode.
Yeah.
Even though I made it zero, so this plate I made it zero now.
Because there's a potential difference.
There is small potential difference. That is the reason it's still receiving the electrons. It's still receiving the electrons. Now that is here now. This graph is coming in this way. We are coming in the opposite direction actually, not from here to here. So when it was plus 5, it was this much. So collector plate potential. So how much it is now? Slowly we are reducing. When you made it zero, it is somewhere here. Now when you made it negative, what will happen? It will repel. This electron is there, right? This is negative. This starts rejecting the electron. So that is why at a particular now maybe at -1 or -2, completely stops taking the electrons. When the electrons are coming, but it stops taking the electrons. Okay. Now this potential is known as stopping potential. Okay. Now take the second intensity, like this one, this case. Now again, what happens? Start reducing the potential voltage. Okay. So at this particular zero, again it is receiving the electrons. But when you make it little negative, it again meets at the same point where this where the first intensity met. The third one also we are doing the same experiment. Again it came to the same point. That particular point is known as stopping potential. And also for one particular color, suppose I have used only yellow color every throughout. Okay. So one particular color, it has one stopping potential.
Even if it has
different intensities, exactly. Even though it has different intensities, then also it has one particular stopping potential. Understood now? Is that clear? Not all this? Then we'll go to the cutoff for only saturated current of that also I write the definition. Is this clear?
So what do we write as a definition?
Yeah. This is the effect of first write this one. Then I'll write what is stopping potential. Then what is saturation current? We'll write all this. Now, what is the definition of saturation current? Then most definitions are there in this. Okay, definitions, and after that Einstein's equation, one equation is there. That's it. That's it. Not much is there in this lesson. A small lesson. Okay. Now, and write the definition. So for a certain positive potential, oops, I'm going to take a bit. Let's see. Okay, I'll write it. A certain positive potential. Okay, now see here, for a certain positive potential, of plate A, all the emitted electrons are collected by the plate A. Okay, they are collected. A is collector and C is the emitter. Okay, and the photoelectric current becomes maximum or saturates. If we increase the accelerating potential of plate A further, what will happen? The photoelectric current does not increase, even though you're increasing the plate potential. Like you made it like +5 was okay, maybe a +6, you started decreasing +6, +7. Earlier it was +5.
Yeah.
Even though you increase the plate potential, no, that is a maximum. Even if you increase further also, you're not increasing the current. The current in the ammeter is same. So if you increase the accelerating potential of plate A further, the photoelectric current does not increase. This maximum value of photoelectric current is called saturation current. Understood? This is called saturation. Please note on this. This is the definition of saturation current. There are around 5 or 6 definitions of it. That's it. This threshold frequency, saturation current, and then
This one was for the cutoff frequency.
uh,
This one is for
threshold frequency. Yeah, cutoff frequency or threshold frequency. I have to post all these videos now. I'm not getting time. It became lazy actually. Earlier I used to, even though before I was working throughout, now it became lazy actually. Last one week.
So when you're trying to school,
9th, 10th period.
it's because the timings will change, right?
Timings also have changed. No, being lonely also sometimes. I feel the energy goes low.
So when will tuition be during school?
What time you want to come? It depends on you. First priority is yours. Later only I'll fix the timing. Like 2:30, we are coming around 1:30 is the okay ending time. Okay, so maybe by 2 o'clock I'll be here. 3 o'clock is okay with you? 3.
Yeah, that's fine.
It will be hot. If it is hot, then
We come
it's
with
like
car.
Yeah, we're coming to
We
car.
come with car.
okay.
And for us chemistry, he will.
What time he will take, sir?
He said that he'll put only 5:30.
Okay, then no problem.
Either that or he'll put after.
He can take after it. I cannot take. Yeah, good. Otherwise, I'll make it 4 to 5 so that 5 o'clock he can start.
Yeah, that's also fine.
Okay. For regular days, I will take only for 1 hour.
Okay.
Okay. Friday, Saturday, Sunday, you take 3 hours, 2 hours.
Yeah.
That's not a problem.
Okay.
Working days, I will not. That much energy I won't have.
For us, any time is fine because we don't have
That's
school.
cool, okay.
We only have certain exams.
See, my target is first I will complete this semiconductors part and EMT electromagnetism also I have to complete for this work. Once I am done with this, what I will do is I will do the sample papers.
Yeah.
Problems I am doing, but we'll sit and do sample
Sample
papers.
papers.
I have given some books also to you.
Yeah.
You can use that. Okay, you can bring that also. We will do the questions from that sample papers and also past papers.
Mhm.
Yeah. See, unless and until you are familiar with the past papers, actually the thing is the wordings.
Yeah.
Many students cannot understand what they know the answer, but because they could not understand the question, they lose the marks. It happened with I'm with my past experience. I'm saying when they come and discuss the paper, yeah, this I know, but I didn't understand the question. This is the response from these guys. Many students, I knew this answer, but I couldn't understand the question. That was the reply. So one has to be familiar with the type of questions. What type of questions they are asking. Okay. Next one. Next one is stopping potential. Okay. I'll write the definition. Now the AC for someone.
Yeah.
That's the definition here. No, till the end, for the graph's purpose, I kept that.
Yeah.
Okay.
Okay.
Otherwise, I would have already. Now, next one is retarding potential. Okay. Stopping potential. Stopping potential. V0 or retarding potential. Okay. The minimum retarding potential for which the minimum retarding potential for which retarding potential for which the photoelectric current becomes zero. The photoelectric current becomes zero for a particular frequency. Becomes zero for a particular frequency. The particular frequency of incident light. Frequency of incident light is called stopping potential. Is called stopping potential V0. Stopping potential V0 for that frequency. Okay. Stopping potential V0 for that frequency. Understood? So the minimum retarding potential of anode actually, the minimum retarding potential of anode for which photoelectric current becomes zero. It doesn't mean that, sir, I am taking red color light and I can say it is retarding potential. No.
It's yeah. Only if
Don't go in the
wavelength-
perception that yeah, for red color light it can be a that is not the frequency, that is not the potential. Suppose yellow color it is working.
Yeah.
Now if you what you have done for this anode, we
Yeah.
made it little negative.
Yeah.
Then it stopped taking the electrons, or it started rejecting the electrons.
Mm.
That particular potential is known as stopping
Stopping.
potential. Is it clear? Did you note on this?
Yeah.
Okay, chalo. Then we'll go with threshold frequency is also done. Now we'll go to the next one more graph. Okay. There is effect of frequency of incident radiation on stopping potential. Two more graphs. Effect of frequency of incident radiation on stopping potential now. What was the before? On photoelectric current.
Yeah. Photoelectric
Yeah,
current.
this is the other one. Okay. Clear?
Yeah.
Now, effect of frequency of effect of frequency of incident radiation on stopping potential. If you have any juniors, you can tell them. Okay, like
Oh yeah.
okay, of grade level, who started grade 12 for both physics or math. Okay. Now, so effect of frequency of incident radiation on stopping potential. Now this graph, let's draw this graph and let's see. So mu2, this is mu3, and this is part of function. This is minus v01 minus v04 minus v03. Now, now here, see, effect of frequency of incident radiation on stopping potential. Now what we have done is, now suppose the color is what? I have taken yellow.
Mm.
Okay, with G or B, I, B, G, okay. Now I have taken yellow. Yellow color, suppose think that this is yellow color light, this is green, and this is blue.
Mm.
Higher frequencies. Okay. Now what happened is, for I have fixed my frequency.
Mm.
So now what I have done is I have taken a fixed frequency, like suppose same frequency, fixed intensity. Now this is yellow, this is green, and this is blue. Same intensity. Electron is ejected out. Okay.
Yeah.
Clear? I did not increase the intensity. Intensity is same, but color is different now. So this is the high frequency. The low frequency, high frequency.
Yeah.
I'm going towards high frequency. Now what happened is, Now collector plate, but this is collector plate potential. See, this is positive, this is negative plate, positive plate. The same, this is -5 and this is +5. Like I'm reducing it, okay? +4, +3, +2, +1, 0, -1. Then what happens? It starts rejecting the electron.
Yeah.
This is the stopping potential for yellow color light.
Yeah,
Example. Now, but for that particular intensity of light, it is same.
Same saturation frequencies.
Okay, I fixed the intensity here now.
Okay.
Understood now? I fixed the intensity. You can write here. Intensity is constant. Intensity is constant. Is constant. Okay, in this case, intensity of light I did increase now. Now what happened? The stopping potential was -V01.
Yeah.
Now what I did, I took the second color, green color, with the same intensity, and now it met somewhere at the other point,
Yeah,
maybe
so
the
that is
negative
the-
point.
Yeah, that's the
Maybe this is
stopping
-1, this is -2 example.
Yeah.
I took one more color with the same brightness, blue here. Then it met at some other point. Understood? The meaning is what? Whatever may be the, suppose above the threshold frequency, any for the same intensity of light,
Yeah.
above the threshold frequency, for any same intensity of light, for any color or for any frequency,
frequency.
the saturation
The
current is
saturation is
same. Number one, saturation current is same, but stopping
Stopping
potential
potential is
varies. Understood now? Stopping potential varies. Once again, see here, when we fix the intensity, now what we have done, now for any frequency but same intensity, saturation current is same, but the stopping potential or retarding potential varies. Is it clear? So the lower one will be having low negative and the higher frequency will be having more negative.
More negative.
This is less negative, this is more negative. Is that clear? That's it. This is about, effect of incident, frequency of incident radiation on stopping potential. Now, last one is very important. Okay. Yeah, so these graphs are very important. Definitely one question will be coming from the graphs. Okay, one question will be coming from the graphs. Clear? We'll go with the last one. Okay, the last graph. Okay, now the last graph says that, what is it? It is the same one. Now, can I remove this? This frequency is mu 0, this frequency is mu 0 dash. This is stopping potential. Now, here we say that, okay, this is frequency of incident radiation versus stopping potential. Now, I'm taking for metal A. Forget about metal B for some time. About metal A. Now, what happened is, now this is the threshold frequency. This is the threshold frequency for that metallic surface. This is metallic surface. This is threshold frequency. As I'm increasing the frequency, stopping potential is also increasing. The previous you have seen that.
Yeah.
Like this, you have seen, right?
Yeah.
Stopping potential is also changing, right? So as you are increasing the as you are increasing the frequency, so maybe it is here, it is maybe yellow color light, maybe this is for
Green.
green color light, this is for blue color light, this is for violet, maybe like this. As you are increasing the frequency, stopping potential is also increasing. Understood? So here also same thing, maybe some other metal you have taken, this is a higher frequency.
Okay.
Some other metal it is, maybe it is having very little higher frequency. Maybe for this, green is the starting color. Green is the starting color. This is blue. This is violet. Maybe it is like this. Understood now? So this is green. This is blue. This is violet. So it is going in that way. So the meaning is what? As you maybe for this metal A, metal B may not be having the same starting or threshold frequency. It is different for different metal. Not only frequencies now, it depends on the metal also, metallic surface also. Some metal emit quick electrons, some may not emit quickly. Understood? So that is the meaning of that. Okay, not on this. But this graph is very, very important. Why? From this we found out the Planck's constant.
Oh, okay.
From this graph, we found out the Planck's constant. Actually, this was first explained by Max Planck also. So, Albert Einstein used the same phenomena of Max Planck, and he went ahead with the theory. Okay, if you can find out, I'll just show you that. So, it is meeting at where? Here, somewhere at 50. See, this one is meeting at 50. Done. So here we say this. What is this 50 called? Work function. Yeah. Do you know what is work function?
It's
The minimum energy of incident light, or the minimum energy so that the electron can be brought from the ground level to surface of the metal. Surface of the metal. That is said to be work function. Okay, I'll write that. Work function of a conductor. So this completes all the four definitions. Okay, or four different graphs. Four different graphs. Okay, clear with this? Now, how do we find out that? See here. Here there is frequency and here there is V0, right?
Yes.
If you find out the slope, what will happen now? Find out the slope. If you find out the slope, so we get V0 by nu, right? Y is equal to, suppose we are writing y is equal to mx plus c. Y equal to mx plus c. What is y? V0. Y that is what? V0 by nu0 into x plus c. That is 50 is the constant. We'll see this. Okay, how it comes. Okay. Now, okay, now we'll continue this. Now here, see the energy. This is the light, okay, and this is E equal to what? H nu, and this is phi, and this is half mv square. This is the kinetic energy of the electron.
Yeah.
Is that clear? Now I'll write the definition. Work function is phi. Work function is phi, denoted by phi. What is work function? Work function is the minimum energy required by an electron. The minimum energy required by an electron to come out of the conductor surface. To come out of the conductor surface. To come out of the conductor surface. That is said to be what? Work function. So how do we write here? H nu is equal to phi plus k max. Okay. H nu is equal to phi 0 plus k max. What is phi 0? Phi 0 is the work function. Okay. Phi 0 is the work function. So what is generally phi 0? Phi 0 is equal to, can be written as H nu 0. Can we write like this? Phi 0 can be written as H nu 0, right? Can we write like this? Because that is a work function, yeah. Minimum energy required. So I am replacing this. So H nu is equal to what? H nu 0 plus K max. So we can write now K max is equal to what? H into nu minus nu 0. Can we write like this? H into nu minus nu 0. This is one more formula. H into nu minus nu 0. H into nu minus nu 0. So what will happen here? If H nu is greater than phi 0, what will happen? Nu is greater than nu 0. Okay, nu is greater than nu 0. So we have nu 0 is equal to what? Phi by h. Phi 0 by h. Nu 0 equal to phi 0 by h. Yeah. Now this is the one. This is not a derivation. Actually, it is to derive different formulas actually out of it. Now we have one more formula. What is that? So now suppose. So you know maximum. See, kinetic energy. Can we take kinetic energy as? We took kinetic energy. Can we written as work done? Work done. Both are having the same dimensions, right?
Yeah.
So if you go back to electrostatics, V is equal to W by Q, right?
Yeah.
W is equal to VQ. So I'm writing here W is equal to V0 into E. Can I write like this?
Yeah.
Charge of electron and V0 is what? V0 is what? Stopping potential, yeah. V0 is a stopping potential. Now I'm converting this equation to another equation now. What is that now? I'm using this equation. H nu is equal to what? Phi 0 plus V0 into E. Clear? Now what is V0? V0 into E is equal to what? H nu minus phi 0. V0 equal to what? H by E into nu minus phi 0 by E. Now see, it is in the form of y is equal to mx plus c. What was there on x-axis? See carefully. Nu was on x-axis. V was on y-axis. Stopping potential was on y-axis. Right. So what happened now? This is what m value now. M equal to what? The line was like this. So we found out the slope. So what is that now? M is equal to here slope equal to h by e, and constant y coordinate is what? y-intercept is 5 0 by e.
5 0 by e.
Understood now? So this is how we found out the Planck's constant from the equation. Got it? That's it. So now we have almost all 3 to 4 equations, right? Related to the Einstein's equation. Yeah. Now we'll do some numericals on this now. Okay. Then we start with example questions here. These 3 questions: 11.1, 11.2, and 11.3.